and we're wrapping things up. This is essentially the graphing principles that we learned. We learned that when you tweak the equation just a little bit by replacing every single x with a constant times x, we know exactly what happens on the graph. It gets compressed this way. Same thing for y, gets compressed or stretched this way. We learned about flipping, and we learned about shifting. Replacing x with x plus 2 shifts it to the left 2. Replacing y with y minus 3 shifts it up 2. And similarly for other constants. These were the graphing principles that we learned. This is a nice section because now we get to talk about, we get to put it all together. I know it seems like we put it all together last section, but today, this time, we really get to put it all together. One of the things I want to talk about is what we didn't learn, the principles that we didn't learn. For example, we never learned in our section what happens if you replace x with, say, something like x squared. What in the world happens to the graph? Well, all bets are off. We didn't get to that one. You'd probably have to pay extra money to get that lesson. That's not one of the basic things that we learned. Neither did we learn what happens if you replace x with, say, something like x plus cosine x. X. So there's a million things that we didn't learn. And it is incredibly important that you realize exactly that the only graphing principles that we learn are these. So when you have these tweakings on the equation, then you know exactly the consequences on the graph. When you have any other type of tweaking, say for example, suppose you replace a cosine x with a 7 cosine x on the equation, well, all bets are off. You know, this is not one of the famous tweaks that we learned. So we don't really know. We didn't study that. You could conceivably study that, but that's not where we're headed. Similarly, if you replace, say, x with, say, x plus the square root of x plus 7, that is not one of the famous replacements that we did. That's not one of the famous tweaks. So the moral of the story here is the only type of tweaking that we did is exactly the ones we did on this chapter. Nothing else. If you've got other types of tweaking, all bets are off. You're on your own on that one. Let me tie that in with today's lesson. Why does that matter? Yeah. To tie it up, I think the best way to do it is to consider the following idea. Suppose that you wanted to graph, let me think. Suppose you wanted to graph something like y is equal to x squared plus 2x plus 1. Okay, that's what you want to graph. Think about that. So you look at this and you say to yourself, well, this is kind of funny because the 1 is next to the x, the 2x, but then you've got an x squared here. By looking at it, you may not really see exactly what the tweaks are. What is a way to proceed? So that's why this section adds just another level of ideas here. And the idea is that sometimes you have to prepare the equation before you actually graph it. Well, you don't really have to, but this technique seems to work really well. If you just spend some time before you get to graph it, if you just spend some time trying to prepare the equation, this will be good for you. Here's a famous way to prepare equation. Every time every time you've got an x squared, which is a degree 2 term, and a degree 1 term, these two can be combined by something famous called completing the square. I'm sure you've seen it in your algebra class. For example, you know that this guy can be written to be, you take half of this, half of 2 is 1, and you square it, and it's 1, and it's already there. If it wasn't there, you would add it to both sides to complete the square, and you can rewrite this equation in a different form. This is x plus 1 squared. And now, when you write it this way, it's all good. Because now you don't have a 1 next to an x squared plus 2x, or you don't have a 2x instead of next to an x squared. You have a 1 next to an x, and that we know the consequences for. That's one of the famous ones. Replacing x with x plus 1 would be a shift left one. So that's the idea here. That's why this section is called prep, then scale, then shift. That's why this is called the prep, scale, and shift section. And the moral of the story is that sometimes you got to do a little prepping on the equation, because if you don't prep it, you might get some strange things here that we've never done. For example, x being replaced with x squared plus 2x plus 1, something crazy like that. We don't know the consequences on that on the graph. That's not something we studied. So by preparing, we can fix that obstacle. Let's get back to it. So just for fun, let's graph this one. We have a blank x squared graph here. The idea would be to go like this. You say to yourself, all right, I want to graph y is equal to x plus 1, the quantity squared. We're going to do the scale and shift. First of all, there's no scaling here because there's no coefficients in front of the x, there's no coefficients in front of the y. So there's no scaling. So if this is the boundary box, if this is 0, at 1 it's 1, so this is 1, negative 1, 1. So then the scaling there's no scale, so it's still 1, 0, negative 1, 1. That's the scale, and this is still y is equal to x squared. And of course the shift here, shift would be y is equal to x plus 1 squared. So it's shifted left 1 spot, so negative 1, take away 1, that would be negative 2, 1, shift left is 0, 0, 1, so my boundaries go from 0 to negative 2, from 0 to 1, and so we'll fit our box there nicely. It's nicely, that's close enough, and then we just draw our graph there. This is just a shift, no flipping going on here, and there you go. That right there, my friends, that's the essence of today's lesson. It's called prep, scale, and shift. Okay. How about we try one for some of the famous trig functions? How does that sound? So suppose you wanted to graph. I don't know. Let's start. You guys want to start off easy? Yeah, let's start off easy. Suppose you wanted to graph y is equal to 3 cosine x. I don't know, something innocent like that. You say to yourself, you know what? What is replacing a cosine with a 3 cosine? Because I know what y is equal to cosine x looks like. This graph I know. The difference here is replacing the cosine with a 3 cosine. And you look to your famous tweakings, replacing a cosine with a multiple of cosine. That's not on our famous list. So we can't use our excellent principles to do this. However, this is the prep, scale, and shift section. So you can imagine we're going to prep it first. Here's what we could do here. In this equation, I think it is legal to divide both sides by 3 and get an equivalent form of the equation. 1/3 y equals cosine x. And now I know exactly what to do here. Replacing a y with a 1/3 y, that is one of the famous tweaks. All you do is multiply all the y's by the reciprocal, which would be 3. So we're in business. That's why this is called the prep, scale, and shift section. So this is the prep part. I just tweak it a little bit so that I can see exactly. Now I'm looking at it, I know exactly what to do. The y's get scaled by a factor of 3. So I'll just do it just for fun. Talk is cheap. Let's do it here. Y. Whoa, take it easy. Y is equal to cosine x. No problem. Super famous. Goes from 0 to 360 degrees. Hey, you know what? I never do radians. Let me do radians just for fun. From negative 1 to 1. And then we're going to do the scale. So we're going to do 1/3 y is equal to cosine x. So to get to here, every y has to be multiplied by 3. So 1 times 3 would be 3. Negative 1 times 3 would be negative 3. Nothing's happening to the x's. So this would be 0 and 2 pi. So it would be, and then the shift, there's no shift there because this was a especially easy one. So it's just 0 from 2 pi, negative 3 to 3. And then the graph, there's no flipping going on there, so it stays the same. Just like that. So then you just graph it. We're going from 3 all the way to -3. We're going from 0 all the way to 2 pi. Can you see that? You can see it. Here's my box. And then my graph. Here it is. Got stretched by a factor of 3. Beautiful. This is almost like the last section where we scaled and shift, but today we added prep, scale, and shift. See? Beautiful, huh? That was way too easy. You guys want to try a more challenging one? Let's try something like this. What if you had take it up a notch or two? How about we take it up infinity notches? Boy, sometimes this thing is too dark, and sometimes. All right. So let's try this. Let's say we have 2y is equal to I don't know. Let's say 4 sine of 2x plus 90 degrees plus 6. Say what? What in the world is that? This thing. Replacing a sine x with a 4 times it. What does that do? That's nowhere on my list of famous tweaks. So I can't. If I'm going to use my famous tweaks, this is not the way to write the equation. This plus 6 hanging out here. What does it happen when you place a 4 sine 2x plus 90 degrees with 4 sine 2x plus 90 degrees plus 6? That's not famous. That's not going to cut it. So here's the game plan. We can take this 6 and move it over there to the other side, way over here to the other side. We'll divide by 4 and move that over there. And here, if we want to do the shift last, we will factor out the 2, so that's 2 times x plus 45 degrees. That's a working strategy. Okay, remember, this was to do shift last, and we'll just continue to do shift last, even though you can do both ways, depending on how you write it. So let's do it. Talk is cheap. First of all, I move the 6 over there. That gives me 2y minus 6 is equal to 4 sine of 2x plus 90 degrees. And already that's better because this minus 6 is closer to the y. This 4 business has to go, the 4, well, I'll deal with that 4 later. This 2 here, if I want to do the shift last, this needs to be factored so that I can see what the shift is. The shift is going to be 45 degrees if you shift last. This also has to be factored, so I'll factor out the 2. That will give me y minus 3 is equal to 4 times sine of 2 times x plus 45 degrees. See, that's looking better already. I know every time I see x plus 45, that's just a shift. If all the x's have been replaced with x plus 45. By the way, if there were more x's on this equation, all of them would have to have x plus 45. If there were more y's, all of them would have to have the same thing, y minus 3, so that it really looks like somebody replaced all the y's with the quantity y minus 3. Okay, this 4 still not going to do it, man. We can't have this 4 here. So the perfect remedy would be to multiply both sides by 1/4. So I could have 2 over 4 times y minus 3 is equal to sine of 2 times x plus 45 degrees. Capiche? And what is that doing for us? Well, it's cleaning it up. There's nothing more. There's nothing else in front of the sign. We can simplify this fraction. This is 1/2 times y minus 3 is equal to sine of 2 times x plus 45 degrees. And that, my friends, that's prepared. Because now you're looking at it and you see exactly what each number is telling you. For example, this minus 3 is shifting it up 3. This one is shifting it left 45 degrees. So then you say to yourself, alright, I'll get the shifts later. I got them. I can forget about them for now. And without the shifts, what it really is just a scaled sine graph. So you say, I can handle the scaled sine graph. That would be easy. And that's it. This is the preparing part. You've prepared it. Okay? So now we go to our sine graph. See, I have, let's see if I can remember it off memory here. I'm getting old. A half y minus 3 is equal to sine of 2 times x plus 45 degrees. Beautiful. So I'll say to myself, you know what, I'll forget about the shifts here. Forget about that, forget about that. If I can get to this step, if I can get to 1/2 y is equal to sine 2x, well, I'll be in good shape, because from there to there, this will have the scale. From there to there, it'll be easy. I'll just replace it, the y with y minus 3, and the x with x plus 45 degrees, and it'll just be a shift. From here to here, it'll be easy. It'll just be a scale. From here to here, it'll be easy. It'll just be a shift. Okay? So easy. So let me think. Alright, let's do it. Talk is cheap. Hey, I said I was going to practice radians. Let's do it. I'm not afraid. 0, 2 pi, -1 to 1. So let's do the first the scaling. Alright, let's look at this. Let me look at these scales. Y gets replaced with a half y. So every y gets multiplied by 2. So 1 times 2 is 2. -1 times 2 is -2. See? I can't believe I get paid to do this. Get paid insane amounts of money. Alright, replace x with 2x. What does that do? Well, every x has to be cut in half. So 0 times a half will be 0. 2 pi times a half would be just pi. There you go. Whoa, I can't believe I mixed it up. 45 degrees. I know what that is. That's pi over 4. I can handle that. So from here to here is shifted up 3. I'll just say up 3. And from here to here, replacing x with x plus 45, you gotta go left pi over 4. Alright, so I'm gonna do up 3 first. So 2 plus 3 is 5. Use your calculators if you need to. -2 plus 3 would be +1. Easy. Easy money. Alright, let's turn these cell phones off, man. Can't believe it. This is such a nice lecture. Being interrupted by phones. Alright, let's do the pi's now. Left pi over 4. So if I've got 0 and I go left pi over 4, well, that would put me at pi over 4. If I've got pi and I go left pi over 4, that will give me 3 pi over 4. You agree? I know you do. Alright, so that's it. Let's just the shift in, the scale shift. Now just do the thing here. Well, by the way, was I supposed to go negative here? Left, that would put you at negative pi over 4. Just checking, you guys. See if you're paying attention. Negative pi over 4 all the way to 3 pi over 4. Okay, from 1 all the way to 5. So I gotta fit my box nicely in there. Let me think. That would be right around here. And right around there. Beautiful. And the graph, of course, I got to check to see if there's any flips. There are no flips. Still the same. So here we go. It goes through there, there. See that? That's why they pay me insane amounts of money. Okay? Just to jam on the songs, do my thing, explain my prep, shift, and scale. My life is good, real good. Alright, you guys want one more example? Take it up a notch or two? Or are you guys good to go? What should we do now? Well, okay, how about we do this one? Are you guys scared? Shouldn't be. Alright, if you got this constant hanging out here, you could always move it next to the y, just so that it's closer to being one of the famous tweaks. That would put you at 2x plus 3 pi. This time I'm doing radians just for fun. Alright, I got to factor out this coefficient if I want to do shift last. And you don't have to. It's just that I could have taught both shift first or shift last. Or I could have just taught shift first, or I could have just taught shift last. My thinking was I'll just teach shift last and then let you guys think about the other ones if you want to, because they all work forever. So you got nothing to fear. So we're going to stay with the same thing. We'll shift last. So if I shift last, I need to factor this out so I can look at it and see what the shift is. I think if I factor out this -2, that would leave you with a -1/2. Easy way to check that is if you distribute this, that would be -2y, and that would be -2 times -1/2, which is exactly 1. So that's factored correctly. And I got 6 here. I'm going to factor out a 2, and that would leave x plus 3 pi over 2. That's right. This looks good because I can already see what the shift is. The shift is going to be left 3 pi over 2. This is good. The 2 I can see that's a scale. This is good. I can see it's a shift. This is good. This 6 is not good. This 6 has to go. So one legal way to get rid of the 6 is to slap a 1/6 on both sides. So that would give you -2 over 6 times y minus 1/2, and that's equal to a sine of 2 times x plus 3 pi over 2. And you can even clean that up. It's -1/3 y minus 1/2, and that's equal to sine of 2 times x plus 3 pi over 2. And now this, my friends, this is nice. This is prepared. This is ready to go. Ready to rock and roll. Cover up the shifts, then all you got to do is a scale problem, and then and scale and shift, and you're done. Watch this. I may be old, but I could just copy. I don't have to remember. Isn't that something? I'll just paste it here. See why they pay me? Okay, so suppose you wanted to graph this. Here's the game plan. You say to yourself, you know what? I'm going to forget about the shifts. I'll leave them last. If I can just get to the scaled version of the equation, I'll be in good shape. So you say to yourself, this would what the scaled version would look like. Sine of 2x. You say to yourself, hey, if I can get to there, that'll be good, because from here to here, you're just a shift away from the answer. 1/2 is equal to sine of 2 times x plus 3 pi over 2. You see the logic? Prep, scale, and shift. That's where I got the name from. I was just working one day and I thought, hey, maybe I can invent the name. Prep, scale, and shift. And I did it. I couldn't believe it. Such a beautiful idea. Prep, scale, and shift. Alright. Let's do it. So from here to here, let's think about the y. What happens to the y? The y got replaced with a -1/3 y. So all the y's have to be multiplied by -3. And there's a flip. Positive y's become negative y's. Just like that. Let's do this. The y's were 1, -1. Let's multiply them by -3. This would put you at -3. The top one, the bottom one would be +3. So there's a flip. Let's do the x's. On the x's. X's got replaced by 2x, so they have to be cut in half. This is 0, this is 2 pi. Cut in half would give you a 0 and pi. Okay? I'll make this stuff look easy, huh? That's what I do for a living. Alright, replacing the y with a y minus 1/2. What that will do is it'll shift it up 1/2. So this would be 3.5. This would be -2.5. That's what happens when you shift up 1/2. I took this guy and I moved it up 1/2. Took this one and moved it up 1/2. Okay? Now I need to work with the x's. What happens to the x's here? The x's have to go. Which way are they shifting? Left 3 pi over 2. So the 0, if you go left 3 pi over 2, would be -3 pi over 2. The pi, if you go left 3 pi over 2, how much is that? Pi, take away 1.5 pi's. That would be -pi over 2. I didn't go to school for nothing. And then all you do is find the points here. -pi over 2, that's about -90 degrees, by the way. -3 pi over 2, that's about -3 90 degrees. +3.5, that's way up here. 3.5 Negative 2.5. That's way down here somewhere. Negative 2.5. I'll make my box there as nicely as possible. Let me think. The box has to go through right around here. Right there. See that? From negative 3 pi over 2 to positive, or to negative 3 pi over 2. From 3.5 to negative 2.5. And now this graph has to fit nicely in there. As it is here, there's no, wait a minute, there was flipping going on here. There was a flip here, so positive y's became negative y's. So now it looks like this. From here to here, there was just a shift, so from here to here, there's no flipping. So the graph has to look like that. Has to go through the center here, has to go through there, has to go through there, has to go through there, has to go through there. Like so. I'll do it right now. I'm not afraid.